Dear friends, welcome to this electrical engineering knowledge sharing channel. We are discussing workshop 6. Today we are going to discuss session 2 of workshop 6, where we will be discussing about the speed control or frequency control of a generator. We have already discussed in session 1 of this workshop about the synchronization of generator with other multiple generators and the various aspects of synchronizations, requirements, and why the requirements are essential. All those points we have already discussed. Today we are going to discuss, in order to obtain the synchronization as well as to obtain the proper load sharing and loading of a machine, how the speed of the machine is controlled and why the speed control is essential. That part we will discuss today. Now, first of all, why we need to control the generator speed or generator frequency, that is we will discuss first. Now, generator is coupled with a turbine, and this total is a mechanical equipment, you can say. Mechanically, it has a mass or inertia, and it is rotating with a certain speed. When a generator is rotating with a certain speed, it is producing power. Turbine is giving the mechanical power. That mechanical power of the turbine as output going as the input to the generator, and then generator out of this input it is producing electrical output, and some part of the energy is getting lost due to friction, other heat, and all this. So if we see this dynamic equation of a turbo generator set in terms of mechanical equation, then we know the normal angular velocity or angular rotational dynamics, how the equation that we know the angular or rotational acceleration multiplied by inertia of the equipment is giving the force or torque. You can say it is a torque, and if we multiply the torque with a angular speed or angular frequency, then we get the power produced per second. Okay, so if we consider the moment of inertia of the turbo generator set, which is rotating together, coupling to each other, if J, then J is the moment of inertia of the system of the turbine and generators, and if omega is the angular velocity of the system, then d omega dt is called the angular acceleration. If this is a angular acceleration into moment of inertia, this is giving the torque. If we multiply that torque with a angular velocity, that will give the power. This power equals to this is the accelerating power. This power is accelerating the machine and producing output power. So this is equal to, we can say that is a P acceleration, accelerating power. What is that? That is equal to difference of mechanical power minus electrical power. That is the difference. Now, so this is omega j omega into d omega dt. D omega dt is change of angular speed with time, that is the acceleration, and that acceleration multiplies by inertia is giving the torque, that multiplies by omega is give the power. That is equal to, you can write down, this is your Pm minus Pe. So this is the dynamic equation of the turbo generator set. Now from this equation it is clear. Suppose the equipment is running with a balanced condition. That means there is no equation running is a constant speed. So there is no change of angular speed. No? There is no acceleration. In that case, this equals to 0 means amount of mechanical power given to the electrical machine is running with that. So this is equal to 0. That means the equipment is running in a steady state condition. At a steady state condition, this is equal to 0. The moment, suppose this is a turbine, this is coupled with a alternator, a generator. This is the system here, this is a coupler, and this is a turbine, and this is a generator. This is the system, it is rotating, and this is giving the output. And turbine is getting input from the fuel. The fuel could be diesel, it could be gas, it could be steam, any type of fuel could be. So this equation now, the moment this generator is asked to produce more electrical power, more than whatever the power, mechanical power coming, the mechanical power coming to the turbine in generator, and if generator is asked to produce more electrical power, that means if PE greater than PM, then immediately what will happen to this equation? This equation PM minus PT will be equal to less than 0. That means P is greater, so PM is negative. That means immediately what will happen? The machine was running with a constant speed. Immediately there will be deceleration, because this become negative means this is the angular velocity, it cannot be negative. J cannot be the moment of inertia, it cannot be negative. So this d omega dt immediately become negative, means it will be, machine will be deaccelerated, means speed will drop down. The moment speed is dropped down, then what will happen? This you have to increase the speed. How you can increase the speed? You can increase the speed by giving the more fuel to the turbine. If you give more fuel to the turbine, it will produce more mechanical power. So this immediately, when this is increased, immediately it will it is maintained same and it is increased. So automatically it become negative. To maintain this equation equal to dynamic steady state condition, you have to increase the PM, that is turbine output to be increased or generator input to be increased. How we can increase? Increase by more fuel combustion in the turbine. So you have to increase the fuel. So in this way, this equation is maintained. That means from this equation we can make out, when a steady state turbo generator set is running with a constant speed or constant angular velocity, that angular velocity omega equal to, we know omega equal to 2 pi n. 2 pi n. N is the angular, it is a RPM, the revolution per minute. So omega is a per minute, per second. If you measure omega per minute, then per minute how much angle it is rotating, that equal to how much? That equal to 2 pi n. N is the RPM of the machine. So that means this omega is a function of speed. That means if we want to maintain the constant speed of the machine despite of change of load, in that case, what we have to do? We have to give the more fuel as per the load requirement. That means the machine angular velocity or RPM is depending on the machine, how much fuel is coming to the machine. That is one part. Second part, this angular velocity, what we write d omega dt, this angular velocity, again the moment angular velocity change, omega change, then how the speed will be changed? We know this omega is a function of angular RPM. Now this RPM, how it will be effect to the frequency of the generator? We know 120 F by P equal to N. That N equal to how much? We said already omega equal to 2 pi N. That means N equal to, we can write down omega by 2 pi. From is it clear that the moment frequency change, the frequency, when there is a d omega dt, immediately there is a frequency change, means there is a RPM change, means RPM change means frequency also getting changed. That means ultimately what we can measure, when there is a loading or electrical loading increases more than is mechanical loading, immediately generator output voltage frequency will get changed. So that is another way we can monitor it. We can monitor by the turbine speed. We can monitor speed is getting dropped. At the same time, we can monitor the frequency of the output voltage, that is also getting dropped. That means when a machine is running in a steady state condition, at that time if we put suddenly more electrical load, then the machine operation, steady state operation will be disturbed. Immediately machine will be deaccelerated, its speed will be dropped down, and the moment speed drop down, immediately frequency of the output voltage of the generator also drop down. So this is the consequences of the loading of the machine. You put more electrical load on the machine, that means you draw more current from the generators. So in that case, the machine will be deaccelerated and it will produce less frequency than that the rated condition. This is why if we want to maintain the frequency of the output voltage, or if we in another way, if we want to maintain the speed of the turbo generator set with the extra loading, we have to control the speed by suitable means. That's why speed controller is essential for this turbo generator set. Now, always we are producing electrical power at 50 Hz or 60 Hz. Suppose a two-pole machine which is operating on 50 Hz, if it want to produce the 50 Hz, then what will be the frequency? What will be the speed? We know speed equal to N equal to 120 F by P. Now, if we want to put 50 Hz, then 120 into 50, and if it is a two-pole machine, then it will be 3000 rpm. That means the turbo generator is said to be run in 3000 rpm. If you want to produce 60 hertz, it will be running on 3600 rpm. That is the way turbo generators are running for the two-pole machine. Most of the high-speed turbo generators, like a thermal power plant or a steam turbine plant, it is generally running at 3000 rpm. This generator is running generally the two-pole generators. So this is the speed equation. That means the speed equation is related to frequency equation. That is very much clear. The nominal speed or the no load condition speed, when there is no load, only machine is running idle, there is the speed. That speed, if we say no load condition or ideal condition speed is n0, and when you load the machine, immediately speed will drop down. Suppose that speed drop down to ns or drop down speed, okay, then the no load speed will be more than ns speed, so there is a drop of the speed. So how much that drop equal to no load speed minus loading full load speed. Then this speed difference to be compensated by additional fuel. So this difference by no load speed, if we divide, or sometimes some of the people they use as a full load speed, if we use that speed difference but divided by this is we call droop. That means speed, this amount of speed is dropped. That speed drop is measured by in terms of either no load speed or the full load speed. Then we call that droop, and if we multiply by 100, we call percentage droop. So this is what definition we'll be using everywhere is called droop. So droop means from the nominal speed or rated speed, how much speed is changed from that position. It could be increased, it could be decreased. If you change the load means if you withdraw the electrical load, then mechanical load will be more, mechanical output is more. Immediately what will happen? Speed will swing up. So instead of ns negative, in that case ns will be more. In that case droop will be negative. So this no load difference of speed from no load to full load, that difference no load to loading condition, that difference divided by no load speed or full load speed. If we divide this part, this is we call the multiplied by 100, we call the droop. So this is one of the definition we will be using. So these are the two important things. Now the moment speed drop down or speed picked up due to putting more electrical load or withdrawing more electrical load, our intention, our voltage should not be changed from the 50 hertz or 60 hertz to other value. We have to maintain the frequency. So how we'll do this? How we'll maintain this frequency? This frequency we maintain through a equipment which is called speed controller or frequency controller. You can say another way, speed controller or frequency controller. That device we call governor. Governor is a electromechanical device which try to maintain the constant speed of the machine or constant frequency of the output voltage of the generator. That is we call the governor. Now this governor or speed controller, how does it do? How does it work? So if we try to explain this thing, we can explain in a better way. How? Suppose, let us consider our daily life. We are driving car, okay? That is also an engine. That is a diesel engine or petrol engine. And then how we control the speed of the car? Suppose you get in the car, start the car. You say the car is running at a 10 km per hour speed. There is an odometer, you can measure the reading. On the odometer, you say the reading is 10 km. So 10 km per hour, you observe. Speed is a 10 km per hour. You observe it by your eyes. So you use your eyes to observe it, right? And then you have some speed in your mind. Suppose in your mind, you are planning to run the car with 100 km per hour. So that is your target value, 100 km per hour. It is in your mind, in your brain. In your brain, it is lying over there. So you want to run the car with 100 km per hour. Then what will do? Then once you see the 10 km per hour and your intention to run 100 km per hour, this is in your memory, then immediately you will calculate how much difference I have, that is 90 km difference there. So I have to compensate the 90 km. So what you will do? Immediately you will press the accelerator by your leg, and that accelerator will open the fuel valve and it will allow to go more fuel, and it will go from 10 km per hour, it will reach to the 100 km per hour. the moment you see the odometer reading is 100 km per hour again by your eyes, then immediately you will tell, okay, I am now right. I will not increase the speed anymore. So I will maintain this speed. That means your brain will tell your leg not to increase. That means how many things are working here? First is a 10 km per hour speed that is to be measured. Who is measuring? Who is the sensor? Sensor is the eye is the sensor. Then eye sensing this, what it is doing? It is wire. It is giving a signal through the wire or through the nerve to where? To your brain, means that is a processor. It is giving signal to your processor, to your brain, that you are running at this 10 km and your brain already has a signal. The brain knows that I have to go to 100 km. So immediately brain will calculate the 100 km, 10 km difference. It will calculate 90 km. 90 km is the difference of speed, and that is a negative speed. I am running with a negative low speed. So immediately brain will give signal to the leg through the nerve. Again brain will give signal through the wire to the leg, means through the nerve to the leg. You press the accelerator more. Then immediately leg is a control element. So it will press the accelerator, means the control element will acting on the accelerator. Then accelerator is opening the fuel valve. This is the engine compartment and there is a fuel valve over here. This fuel valve is getting opened. This is the fuel valve. This fuel valve is getting open. Its signal is coming from through the accelerator, through the leg and accelerator coming to the fuel valve. Fuel valve is getting open and more fuel is coming to the engine and engine speed going up. So these are the way this car is driving. Here in the case of turbo generator set, the same way it is working. In the turbo generator is the same thing. We have to sense the present speed of the turbo generator set or present frequency of the generator. Then this turbo generator, the control element, it has a brain or processor where already required speed. Suppose 3000 RPM, 2-pole machine, 3000 RPM speed is required or 50 Hz frequency is required, that is already put there. So this sensor, there will be a sensor who will sense actual frequency or speed, and that frequency and speed will compare, processor will compare, like a brain it will compare with the actual speed and the set speed. If there is a difference, either positive or negative, immediately processor will calculate the error signal or the difference signal. And if the difference signal is very small amount, then the difference signal will be further controlled by control processing. And with the control processing, there is three different type of controller is available. We call it proportional controller, integrate controller, differential controller. So as per this controller, either 1, 2 or all three will be operating on this error parameter. Then it will be control signal will be generated. That control signal will go to where? It will go to the controller, which will be a final control element, and the final control element will take the action to compensate the change of speed. This way, this speed controller works. So if you look into the speed controller, so speed controller has all these parameters, all this gadget, lighting, it interface with all these parts. So if we said speed controller, we said controller. So in the controller, one part is called the input section. So input section, what is there? Input section is suppose this is a turbo generator set. This is a turbine coupled with a generator. Now in the turbo generator set, the first part is we have to sense the signal, or we have to sense the speed. How we sense the speed? Before we used to buy tacho generator. We put the tacho generator, when the turbine is rotating, it will capture the rotational speed, convert it to DC signal. We can also have a magnetic pickup. The magnetic pickup, how it will work? It produces actual output. If we there is a shaft is rotating over here, and there is a flywheel. There is a flywheel. On the flywheel, there is a teeth, and the magnetic pickup is putting in this way. Suppose this is the magnetic, it is going inside the enclosure through a cutout, and then there is a gap about 25 millimeter, very small gap is there, 0.25 millimeter gap. A small gap is there between these two. So when it is rotating, when this teeth passing over there, then it is producing a signal. The signal frequency will be divided by the speed and the number of teeth. If there is a number of teeth is X number of teeth, and if it is rotating with any speed, so this will be the frequency of the magnetic pickup. So the magnetic pickup will send this frequency signal. It is generated the signal. That signal, AC signal, will come to the controller. That will give the present speed or actual speed of the turbo generator set. So this device we call magnetic pickup, magnetic speed pickup, magnetic speed pickup unit, MSPU. this MSP will sense the turbine speed, and that speed will come to the control element as an input, and this control element has already set up. Suppose we have already put that required speed or the said speed. Said speed how much? That is the speed we need. This is the actual speed. This is a n actual speed. This is the said speed. We said that suppose we want to run the speed with 3000 rpm. So n is equal to 3000 rpm. And this speed actually it may be 2900, it could be 3100 depending on the load. That speed is coming over here. So this is a input device. Then what is doing? The input device comparing these two and it produces a error signal. That means input, first part of this is a input device, where in the input device there is a actual signal is coming, NA is actual speed is coming from the magnetic pickup, and it is already a reference signal or NS set speed is already input over here, it is already there. Then the second part, this two signal will come, that is a NA difference NS. This, there is a processor over here, or you can say this is a comparator. This will compare these two signal, then it will create a error signal. It will create an error signal, positive, negative, one error signal it will create. That error signal will come over here. Now this error signal now will be controller. What type of control philosophy we are using? It is a proportional controller, or it is a DI, DDT controller, or it is a integral controller, or all these three or any two. Depending on this controller function, it will create a final control signal. This will be final control signal. This final control signal will be very weak signal. So in the case of turbo generator set, ultimately the signal what it has to, he has to open the fuel valve. The fuel valve, how it is operating? Fuel valve is actually, it is a motorized valve. It is MOV operated. There is an actuator. So actuator is taking the current and it is rotating. As you send more current, it will rotate more. It is a control valve, but it is a motor operated control valve. So if you give less current, it will rotate less. So this needs a actuator, a motor to be rotated. So this signal will be very poor signal. So this signal need a further amplify. So this signal will come to the amplifier. So this is amplifier. Usually amplify. It is about in the range of 15 ampere range. In that range it will come up. Then after all the processes, there may be harmonics or some enormous other signals are there. So it needs a proper filtering. So after filtering, it will come to the actuator. Actuator means that fuel valve motor. It will come to the motor and motor will rotate. So this way the control loop is operating. So control loop is operating how? There will be a input section in the controller. That controller will take this input signal and the reference signal, they will do the difference. Error signal will generate. The error signal will be further. Control action will be on the error signal. Then final control signal will generate. Control signal will be amplified and then it will filter out, and then this final signal will come to the actuator. This way this control loop will be operating. Okay. Once this signal actuator is working, that means in the input device we can now, this is the control loop, we can delete this part, and here we can show what then this comparator is here. This is your comparator. Okay. After the comparator, so this is your comparator section, or you can say it is a processor section. This is the input section. This is the processor section. Then what is there? Then there is a output section. Okay. There is a output. This output when going, it is going to the accelerator or actuators. Actuators, it is going to the actuator motor output. Then this total device, if it want to work, all this thing work, it needs some control supply. So there will be a power module, there will be a control supply module over here. So this will be actually, it is going to output. This is output module, and then there is a control power module. Control power module means it will receive the control power to operate this thing. Then this governor, it will come afterwards. It has some different mode of operation. It mainly two mode of operation it has. One is called Droop mode operation. Another is Isochronous mode operation. So that operation we can interlock with some breaker contact and all these things. So that contact interface is there. Again, this governor, you know, when there are multiple generators running, one generator speed is getting changed, and if it is coupled with other generators or parallel in other generators, this change will be transferred to the other machine also. So there will be a communication between amongst the governor of the other machines. So there is an interface from this governor to other governor or load sharing module, you can say. There is an interface, and then this output, when this output comes, it gives a feedback. It gives a feedback to the original unit. I have reached to the original speed. So that feedback should come. So accelerator, this device will stop this processing. That signal will also come. So all this part will be in the governor. So governor has how many parts in the governor? That means governor has an input module. It has a processor module or the algorithm module where this all processing will be done. Then second element is the output module. It has a control supply module. Then it is a setting module where the various settings are there, and then it has a interface module. These are it is a typical one governor I am talking about, but make to make it could be further more parts could be there depending on the various type of governor. I am talking about electronic governor. So these are the various part of the electronic governor. So if we look into the speed governor, which is controlling the speed governor has mainly 5 sections. One section is the input section. This is if you divide the controller, then you can see controller how many sections. There is the input section. This is the input section where the actual speed from the magnetic pickup it is coming. That is the actual speed, and there is a reference speed. That is NS. This is coming from magnetic pickup from the field. It is on the turbine, and this is in the control room. This is a magnetic speed pickup. It is coming from magnetic pickup, actual speed. So this part is a input device. Then we have a processing section or processor, where it is all the calculation, everything is done. Then and the error signal is producing, and the error signal is further getting. There is a hardware part where all the amplification, all this is taking place. This is a hardware electronic part, you can say. Okay. Then there is the output part where the actuator is connected. This is again on the turbine. It is actuator or the motor, you can say MOV, which is connected to the fuel valve, which is operating the fuel valve. So the output is coming over here. Then what we have? We have a setting section where we have mainly 2 types of setting. One is called Droop setting, another is called Isochronous setting. And this Droop setting again, it can be interface with the breaker and output, all these things to include the interface with other breaker, or to activate the Droop mode or isochronous mode. There is some arrangement, there is some contact incorporation provision is there. That is called setting interface. And then is a final interface section where it can be connected to the other governor or load sharing module and all these things. Okay, these are the various section of the typical governor. How this governor signal or the speed signal difference, how it will operate the fuel valve. If we look into one of the GE machine, so this speed change, what we said, speed change is related to the fuel reference setting, or you can say fuel stroke. How much fuel valve will open close, that difference of the speed difference. As per GE, we call it fuel stroke reference number. This terminology we use, FSNR, that is called fuel stroke reference RN, fuel stroke reference number. That is equal to some constant into what we said, that is your reference speed or steady state speed minus actual speed plus K1 plus K2. So it is depending this how much the fuel valve will open, that is guided by this equation, that is proportional to the difference of speed. And if you see, this is equal to y equal to mx plus c, this type of equation. That means if you plot this equation will be like this. This is equal to c amount, and this is gradient is m. That is the gradient K1. This is a K1. So it is a straight line cutting their y-axis. So this proportional, that means as the speed difference is more and more, fuel valve will open more and more. That is a fuel valve stroke reference number. So these equation follow final control element of the turbine. So how much fuel will go, it will be difference by this. So this equation is maintained in the governor to calculate this control signal. Okay, this is one of the small point I discussed. Now we will come back to this this governor. It has we said that governor has a 2 mode of operation. Okay, one is called Droop mode, another is called isochronous mode. What is the difference between these two? Now, in case of governor, as it is speeding the control, how the operation mechanism is working here. The moment governor understand there is a change of speed, immediately governor will give a signal to compensate that speed. Immediately what will happen? As per this equation, governor will give final signal to the actuator to open the valve. Valve will open, immediately fuel will go and it will change the frequency. It is for the single machine we are talking about. Suppose there is a single machine is running and it is carrying load, and suddenly this is one load, suddenly one load has come up. This is the new load. Immediately what will happen? The generator speed or frequency will drop down. The moment frequency drop down, immediately governor will pick up. Governor is sensing the speed. Governor will immediately create this difference signal, and then governor will give a final control element to the FSRN, fuel stroke reference number, or this is a angle. This will divide. It will decide how much angle the fuel valve will open. Immediately it will give the signal depending on the difference, and immediately speed will come up. More fuel will go, speed will come up. So instantly the machine speed will come up to the normal speed. So this, if the operation is this way, then we call it is a isochronous operation, because in this operation maybe some millisecond it will come back to the normal speed very quickly. In this mode, as it is directly sensing the speed and giving the signal to the final control element, it is a very quick, and in that case you will not feel the machine has changed the speed. This operation is so quick, you will not physically, you will not see there is a change of frequency. So this mode of operation we call is isochronous mode. Okay, that means in the isochronous mode you will not feel, though there is a, with the loading there is a change of frequency, but practically that frequency change you cannot observe physically. It will instantly, the frequency will pick up. It will instantly it is drop, immediately instantly it will pick up. And if this operation done in that way, it's called isochronous operation. The problem in the isochronous operation, what suppose there are two machines. Suppose there are two machines. This is one machine, then there is another machine. Suppose there are three machines running in parallel with the same bus. Now suddenly on the bus there is a load coming. The moment loads come in, then immediately frequency will drop down of the bus frequency. The moment bus frequency drop down, immediately all the machine will sense the frequency difference. Then all the machine will try to compensate that frequency, means they will try to increase the speed by fueling, opening the fuel valve. Then there will be competition among the machine who will first take the load. So as all the machines running with the same speed, so there will be competition among the machine, and that may cause the instability of the machine operation. So when multiple machines running in parallel, if you put all the machine governor in the isochronous mode, there will be a competition, and there is a chance of instability of the operation. So that's why multiple machines running in parallel, we do not prefer to run on isochronous mode. Isochronous mode we operate where? When the single machine is running. And number two, it can be possible if all the machines are identical and all the governors is also identical. See, the machines which are running in parallel, all the machines are identical, and all the machines speed controller governor is identical, and those governor has a facility to communicate to each other how much loading they are taking place. In that case, with the cross connection provision and with the identicality, it may be possible to run the machine in isochronous mode. Otherwise, if there is some two machine is new machine, one machine is old machine, one machine governor is old governor, another two machine governor is a two different type of governor. If this is type of situation, then if you put all the machine isochronous mode, it may not be possible to a stable operation, or they get a constant frequency from the machine, and machine can be tripped. It cannot be run in parallel. So only option is for single operating machine or very identical machine with all identical facilities. It may be possible to run multiple machines. Another option, it can be run in isochronous mode when one of the machine is very big. Suppose this machine is a 5 times rating. Suppose this machine is a 5 times rating of the other machine. Suppose this is A machine and this is a B machine. If this machine is P rating, this machine is 5 P rating. This machine is very big. If this type of operation is there, then the biggest machine we can put on the isochronous mode. We can put this isochronous mode, because isochronous mode machine will maintain the bus frequency constant. I said why, how they will do it, because I told you it is very quick. The moment frequency drops, immediately isochronous machine who is running on isochronous machine
immediately he will sense the frequency difference, and immediately it will open the inlet valve and compensate the difference of frequency. So it will maintain the constant frequency. That means, we say another way, isochronous machine is running as a infinite source. So it will maintain the bus frequency. Whatever the loads coming on the machine, isochronous machine will immediately take the load. If frequency will get difference, immediately will compensate. But the other machine, which is a smaller machine, that machine will not take any load. It will not, if this machine, big machine, if two machines are running in parallel isochronous mode, the big machine will take all the load. This machine will not take the load. It will just act as a follower. So in this case, we can put two machines in isochronous mode. But if the machines are identical or is not identical, and one machine, all the machines more or less same size or near about size, one is one time, another maybe one is maybe 1 megawatt, another is 1.5 megawatt. If the governor is not the same, it is not advisable to run the machine in isochronous mode. Okay, so this is the normally isochronous mode as a grid frequency. Grid operator is we consider grid is a isochronous machine, because grid frequency is always maintained, and if some loads come, always grid takes, not the other machine. So here also the same thing. Here when the machines, biggest machine will take the load, other machine will not take the load, and it will be acting as a follower. So mainly isochronous operation we do with a single machine operation, or if it is a identical multiple machines with identical facility, we do sometime in isochronous operation. Otherwise, one big machine, one small machine, if that is there, then we run the big machine on isochronous mode. Other machine we operate generally, if there is a multiple a smaller machine, we put this machine on the Droop mode, and this machine, big machine, we put on isochronous mode. It will maintain the bus frequency. So this is the isochronous mode. Now in case of Droop mode operation, when the machines are not identical, and when the machines governor system also not identical, or if the machine is running in parallel with the grid, in that type of operation, we cannot run the machine in isochronous mode. I said why? Because they will compete each other and machine will go in unstable operation. In that case, we use another mode which is called Droop mode. In the case of Droop mode, how does it work? In the case of Droop mode, suppose the machine is running, I am drawing one curve, then it will be more clear. Suppose this is a 100% speed, okay, 100% speed. So this is a, suppose Droop, it is 104%, you can say 104% speed. So now the machine operation will be like this. This is a 100% load, okay, this is a, you can say this is a, it is a ideal operation. Ideal means minimum fuel operation, means engine is running but it has no load. So this amount, no load is there. This is a zero load point, and this is the ideal operation. Okay, from here it is starts. Suppose now here in this mode, what is happening? The machine is not running on constant speed. When the machine is no load on the machine, it will be running at 104% speed. Suppose this speed is 104. This speed. Suppose I have a 4% droop. It is called Droop mode. We are now discussing about the Droop mode operation. Suppose a machine no load speed is 104% of the full load speed. If that is the case, then in that case we say it is a 4% Droop. Now 4% during, that means when the minimum fuel position engine is running without any load, engine speed is 104%. Now as you increase the load on the machine, suppose we are talking single machine. As you increase the load on the machine, then what will happen? Engine will be deaccelerate. So there will be, the moment you increase the load, immediately suppose you load by 25%. Suppose this is a 25% load. Immediately the speed of the machine will be dropped down to over here. So this is 104% speed with no load. The moment you put 25% load, engine speed will drop down to, suppose it is a 100%, 103%. It is 25% drop is there. You increase the load another 25%, speed will be coming over here. So this may be 102%. Suppose you put 75% of the load, speed will come over here. The engine will be running at 101%. When you load the machine 100%, engine will be running at the rated 100% speed. If the operation of a generator is working on this principle, then we call it a Droop mode operation, because here engine speed is drive or engine speed drop is depending on the amount of load. That's why we call it Droop mode operation. Here machine will take the load as per the Droop setting. Okay, So when you put 50% load, immediately load speed from 104% speed. Suppose 3000 RPM machine, it has a suppose 4% droop. 4% droop means the running at 3120. Okay, that is the no load speed. Now if you put a 100% load, it will come down to 3000. Suppose that means 3000 replica to 50 hertz, and this is replica, not maybe it may be 51 hertz, like that. Now if you put 50%, this is your 3120, 4% droop. Now if you put of the if you put 50%, then what will happen? This will be running 3060, right? For the on 50% load. So at that time frequency will be maybe 50.5 hertz, like that. That will be the frequency. So when you run the machine, suppose single machine running on droop mode, machine is 4% droop. The moment you run the speed, run the machine will be in idle condition, it will be running on 3120 or 51 hertz, suppose 3120 speed it is running. Now if you load the machine by 50%, speed will come down to 3060, okay, and machine will be running with that speed, and corresponding frequency may be 51.5 hertz. Now operator has to intervene. Now operator has to go and he has to drop the frequency manually to get the required frequency of 50 hertz. Without manual intervention, you cannot get the rated speed. Otherwise, machine will be running on 50.5 hertz, and then it will be continuing in this way in the droop mode. It will not automatically come back to the constant speed or the reference speed, as case of isochronous operation. In case of isochronous operation, governor is taking back normally to his speed. But here, manually you need intervention because it is a droop mode operation. The frequency of the mesh output or the speed of the turbo generator set will be decided depending on the droop setting and the loading. So when the load is 100%, it will come back to 3000 means 50 hertz. But till the load is not 100%, if you want to run 50% loading of the machine, natural frequency will not be 50 hertz. So by manual intervention, it will bring back to 50 hertz from that corresponding AVR governor speed. That means when you put 50% load, governor will be running 3060 speed, corresponding frequency. Now after running the and operator will be observing this is the frequency of the bus. Now he has to come back and control the frequency to manually to bring back to the required frequency. So if the operation is machine in this way, then we call it droop mode operation. Advantage of this droop mode operation is machine how much load it will take, it depends on its own droop setting. So if the machine which has a high droop setting, in that case what will happen, this no load speed of the machine will be more. In that case it will take first, it will start to take the load, and then gradually other machine will take the load. But if all the machine has equal droop setting, all the machine will take the load proportional to their rating. That is the advantage of here. The machine will not go unstable. Every machine knows how much load he will take. It will be decided by the droop setting of the machine and the capability of the machine. That can be betterly explained by curve, which we will explain now how the droop parallel machines droop setting work. Suppose there are two machines running in parallel, and suppose both the machines has identical droop setting. Suppose this is your we will drop over here. Suppose this side is the load, this is load, this is the load, and this side is your droop or the free speed, you can say. So suppose this is your 100% setting. It is a 100% speed. Okay. Suppose the machine has a 4% droop. Both the machine has a 4% droop. So this is a 104%, and then minimum will be 96%. So this is the zone of operation. Suppose there is a machine A, his droop characteristics like this. And the other machine, suppose there is another machine, I am writing in opposite side. So there is another machine is a bigger machine. Okay, this is a 100% load for this. Suppose this machine, its total capacity is P1. This is a P1. This is a 100% point. The load point, this is a 100% load. So at the no load condition, speed is both the machine 104% droop. Okay. So suppose it is a 400% means 3000 RPM. So 4% means 3120. This is the RPM at the no load condition, both the machine running on this RPM. Okay. Now this machine is a capacity P1 and this machine capacity is P2. This machine is a bigger machine. Suppose this is a bigger, P2 is a bigger machine. Now when both the machine running in parallel at the no load condition, both machines are speed same. Now the moment you give some load, suppose P amount of load given to the machine, both the machines, how the machine is running, this is one machine, this is another machine running in parallel. This is a bus and here is a, you are putting the load. Suppose this amount load put on the bus bar. Immediately what will happen? Both the machine will try to take the load. This load will be shear as per the machine. Immediately machine will be slow down, right? So the machine, suppose 104%, it dropped down to 101%, 103%. So this machine, this is the 103% line. So this machine will take this amount of load. This amount of load will be taken by this machine, and this machine take how much load? This machine will take this amount of load. This is the load. This machine will take this amount of P. Suppose it is a P2 dash, this is a P1 dash. This total P equal to P1 dash plus P2 dash. That means when 100% load, you give a suppose 25% load, total load means P1 plus P2. This is the total capacity. This into 0.25. This amount of load is P. When this amount of load P is given, immediately P1 machine will take 25% of its capacity, means up to this point P1 dash, and this machine will take 25% of its capacity P2 dash. So total P1 dash plus P2 dash equal P1, that equal to 25% of the capacity of the machine. When you put 50%, suppose you put 50% load power, when a 50% load you put 50%, 0.5 into P1 plus P2. This amount of load is put over here. Then immediately what will happen? Both the machine from the ideal condition, it will come to higher. 50% means this is a 50%, it is a 50% line. Its speed will come 102%. So 102% if you put a line, so this will be coming this. So this machine will take this amount of power and this machine will take this amount of power. When you put 100%, then what will happen? It is a 100% line. So this machine will take P1 and this machine will take P2. So though the machine has unequal capacity, but it will be sharing the load as per their capability of the machine. So this is the advantage of the Droop operation. So when the machines are not identical, different rating, governors are different, so they will act in a Droop mode. And in this case, another point, suppose two machines are running in parallel, but they are not on the same Droop setting. In that case, what will happen? If the Droop setting is not same, the machine which has a higher Droop setting, that will take the load first. Till the machine, that particular machine on loading, it is not coming back to the other machine Droop setting. How is it? Suppose this is a machine, this is suppose 104%, one. Another machine has a 102% Droop setting. Suppose this is two machine. So this machine and this is your 100% line. Okay. So now this machine characteristics, Droop characteristics like this, and this machine Droop characteristics like this. This is 100% line, okay? This is 100% speed line, and this side is load. Here you see, when the machine is running in no load condition, this machine, what is the Droop? 102%, and this machine 104%. So if you draw a line from here, what is happening? It is not, this machine is not taking any power, because all the power is coming to this machine, because this machine has a 104% Droop. Due to the loading, the Droop will drop down, the machine speed will drop down. When the machine speed drop down to 102%, that means 50% of the machine is loaded. This machine is 50% loading is already done. Suppose this is a 50%, this is a 50%. So when 50% loading of this machine has done, then the machine has dropped down 104 to 102%. At this point, this machine, suppose this is a machine and this is a B machine. At this point, both the machine has identical speed. Both the machine has 102% speed, and then it's come down to about 101%. Then what will happen? This machine will take this amount of power, this machine will take this amount of power. That means you see, total most of the mesh power will be taken by the big machine who has a higher Droop setting, and the other machine will take less power. So if the Droop setting is not identical, we cannot expect the loading on the machine, sharing of the load will be identical. In that case, load sharing will be different. So if we want to run a machine on sharing of load proportional to the capacity, both the machines should have an identical Droop setting. And here also, that is the required. So this is the Droop setting and the Droop operation. Okay. Now we have already discussed, in case of Droop mode of operation, it is a slightly slower than isochronous operation, because in the case of Droop mode operation, machine is running at no load speed. Suddenly loads come. Each governor will take the signal and they will calculate the signal based on the present load and how much load difference. Then they will take the load, and to take the load they have to give a signal to open the fuel valve proportional to their loading. So it will take slightly slower. So that's a Droop mode operation is slightly slower operation, but it is preferable to use this operation when there is a multi-wheel machine of different rating, different type of speed controller. In that case, Droop mode operation is important. Second point, if a machine is running with a grid, suppose this is a grid, suppose this is generator is running on a bus, and this bus is connected to a grid. This is a grid, infinite grid. Suppose this is a grid. You know, this suppose this is one of the island, and this machine running in parallel to this. In that case, this machine, whatever the, and this is coming, these are the bus where the loads are connected. Whatever the loads are connected over here, this load will be taken by the grid, because grid is maintaining the frequency. Grid is an infinite source. You cannot change the. So in that case, it is infinite frequency bus. So this bus frequency you can change it, cannot change it. In that case, what we do? We put the machine on the Droop mode. So this, if and Droop mode, and we take this generator, suppose 100 megawatt generator, and we have a load maybe 400 megawatt. This generator may be loading up to 80 megawatt. So what we do, by changing the Droop, by controlling the Droop and frequency, we load the machine 80 megawatt, and then we maintain in Droop mode. Then if in addition to 80 megawatt, whatever the new loads are coming, all the load will be taken by the infinite bus. So grid will supply the power. This machine will not take any power till this grid is not telling this machine to take the power. In this case, this machine will be operating manually Droop. Controlling the Droop, we can increase the capacity up to 100 megawatt, not more than that. So any loads come on the machine, grid will take. Grid is infinite, which is controlling the frequency, that will take the load. So in a brief, when a machine running in parallel with one isochronous, one system isochronous, another is Droop mode. In this isochronous system will maintain the bus frequency. Droop mode machine will not take any extra load till the other system or manual intervention is there. So that is a combination of the isochronous and the Droop mode operation. Okay. Now, if you come to the particular governor, then from the various discussion we have made, we can see the different aspects. There are various settings available on the governor. First is a governor. We have said that governor has a reference signal or reference speed signal setting is there. So number one setting will be reference speed. You want to run the machine 50 hertz frequency or 3000 rpm or 3600 rpm means 60 hertz. The reference signal or speed to be setting should be there. That is one setting is there. Number two setting, what is there? In which mode you want to operate the machine? You want to operate the machine is Droop mode or isochronous mode. That selection should be there. That setting also there. Then number three, if you want to mode in the Droop mode or isochronous mode, what percentage of Droop you want to run? That Droop setting will be there. It is a mode selection. This is a Droop or isochronous mode selection. Next setting will be Droop setting. You want to run the machine 102% Droop or 103% Droop or 104% Droop. The Droop setting should be there. That is another setting. Number four setting. This control voltage, what control voltage? Maybe in the same governor there is a multiple voltage available. The governor you can give a 48 volt DC, 24 volt DC, or it's possible to give both AC and DC signal. So that setting will be there. Auxiliary power supply setting should be there. Auxiliary power supply provision. Which supply you have to give, accordingly you have to set the switch accordingly. That is number four. Number five, this governor, this we have given the Droop setting in this upper Droop and lower Droop. 104%, if it is a 4% Droop, that means it could go up to 104%, it can go up to 96%. That is the range. Suppose I have a 4% Droop, means in the positive side it will go 104%, negative side it will go 96%. It is a 100% line. So if suddenly the machine goes above 104%, then we call it the overspeed condition. If it is go below 96%, we call underspeed condition. The overspeed and underspeed condition, we can monitor and we can give the protection. If the machine run on overspeed, then there is a problem with the it may happen to problem to the machine, both the overspeed and underspeed. That's why overspeed, underspeed running machine is not advisable or not desirable. So we give the protection setting for overspeed trip and underspeed trip. Both setting we provide. So there is another setting available, overspeed and underspeed. that setting is also available in the governor. Then governor has another setting. Governor, we can, the governor nowadays is digital governor. It has another setting we call a stability setting or gain setting. Okay, what is that gain setting? Now, due to the setting, governor will be very fast in operation or it may unstable. So if the machine is vibrating, suppose due to the governor it is giving the fuel in such a way, machine is vibrating or machine is not very much stable. In that case, we have to increase the stability or reduce the gain. So there is a setting we call as gain setting. By adjusting the gain setting, we can make the machine more stable. It is operating, it is available in the governor. Then the next setting available on the governor, that is the governor, we can control the governor remotely also. As we said, the governor, there is a governor raise lower, governor speed we can increase or decrease, and that increase or decrease is done through a potentiometer. There is a resistance in the circuit. By changing the resistance, we can change the current, and which will ultimately increase or decrease the speed of the machine. Because speed of the machine is decided by the actuators, and the actuator is operating on what basis? Basis of the output current. By inclusion of the resistance in the circuit, we can change this current, means we can change the actuator position. So by this resistance, we can control locally on the governor itself. This can be possible. Suppose this is a governor and there is a potentiometer, variable resistance, and this is we can control by a knob on the governor panel itself, or we can take this lead to the remote, and the remote we can put a actuator on resistance with a motorized resistance. We can do by motor with a small step motor. We can change this resistance step and we can change the signal, or remotely also by manually we can do from the remote panel. So that interface also possible. That interface also we can include. This include how this resistance is a multiple setting. We call it a actuator setting. It is a full opening. Is the acceleration setting. If you change in the direction of acceleration, it will increase the speed. In the deceleration, it will reduce the speed. There is the intermediate position of the potentiometer. That is the intermediate position. It will gradually speed. So there are various potentiometer available on the governor for adjusting this rheostat. So that is also available on the governor. These are the various settings available with the governor. So with this, we can, these are the various settings, and by adjusting the setting and by trial, we can commission the system so that the stable operation can be ensured. Okay. So these are the various applications. So in a brief, we can say governor is a device which is controlling the speed of the turbo generator set, and through the sensing the input actual speed and with the reference signal, and it has a two mode of operation. One is isochronous mode, another is droop mode. Isochronous mode we operate generally in the single machine, or in case of two machine, one is a big small machine, one is a big machine, another is a small machine. In that case we use the isochronous operation. And if the machines are not identical, multiple machines to be run in parallel with the different governor configuration, different speed, different machine configuration, in that case we go for the droop mode. And this governor, previously the governor was a hydraulic type. This governor could be mechanical governor. Nowadays all the governors, mainly electronics or digital governor, it is very fast in acting with a lot of setting provisions, and with the governor operation we can make the machine speed or frequency stable. So this is all about the governor. And droop mode is slightly sluggish or it is delayed, but isochronous mode is very quick. And isochronous mode mainly operating three operation, single machine operation, or a machine is operating with the grid. In that case, grid will be running on isochronous mode, or identical all the machines running in isochronous mode. If all the machines are identical and with the same governor, everything, that machine can be run in isochronous mode with a cross connection amongst the governor. So these are the various part of the governor and the speed control of the machine. Next session we will discuss about the voltage control of the machine or AVR control. Okay. By the governor setting, what we are doing, actually we are controlling the active power. By changing the speed, we have already shown that power equation. So when power requirement is getting changed, we control the speed. If we increase the speed, we can get more power from the same machine. If we reduce the speed, we can get less power from the same machine. This is an active power control device. So governor we are using for controlling the active power. As we have said that any power, apparent power has a two part. One is the active part, another is the reactive part. Governor is used for the turbine active part control, which is given by the turbine to the alternator. So you have to keep in mind, governor is a speed controller, but is actually controlling the output active power of a alternator or generator. Thank you very much. We will see in the next session. Thank you.